In this video, we're going to be looking at light spectroscopy of mixtures as an example problem with this. My recommendation to you is to pause this video first and try to solve this problem on your own before you listen to me, and then see where you got to and see if we match up right in our thinking, or where you got stuck, see how I get through it. So give me a pause and do that. Okay, at this point, you either have gotten your problem done or you got to a place where you're just like, I don't know where to go on from here, Dr. Leslie. So let's take a look at this. So we have a mixture of two compounds, A and B. So we're going to assume those are the only two things present. We don't have to worry about anything else. We find their absorbance at two different wavelengths, 460 and 540. We want to know what the concentration of each species is, and we're given the molar absorptivity of each of those compounds at each of those wavelengths. So this will let us set up a system of equations where we've got two unknowns and two equations. So an important point to remember is that absorbance is additive in using Beer's law. So all the compound A will contribute a certain amount of absorbance, and compound B will commit another amount of absorbance, and we just add those two together. So this is assuming there's nothing about A and B that would cause them to react with each other or make any changes. So assuming these are two different absorbing species that aren't going to interfere with each other, and that our absorbances are in somewhat reasonable ranges to use Beer's law. So those are the assumptions we're making with this problem. So to set up my two equations, all I have to do is recognize that my absorbance at each wavelength, so let's say at 460, is going to be equal to the molar absorptivity at 460 of compound A times the path length times the concentration. I didn't mention a path length here. Assume a path length of 1. We tend to do that a lot because we mostly use cuvettes that are 1 centimeter. So do assume that. And if you got stuck there because of that, you can pause now and try to solve through it. But yeah, I'm going to use this path length of 1. So the concentration of A, and then I'm going to add the other species. The molar absorptivity of 460 of B times path length times the concentration of B. So those are both just going to add up together separately. And so this gives us an equation of, so for A, and what I'm going to do is I'm not going to put in the units because I'm going to show that they cancel out. So B is in centimeters, so centimeters times inverse centimeters cancels out. And then molarity is where our concentration, and this is inverse molar, so those cancel out. So the units are there, they're just going to cancel out here. So just to fit it in the line, I'm not going to write them next to it, but they do cancel out here. So we have 2,750 times 1 for our path length times a concentration that we don't know. I'm going to call it concentration A. I was going to use an A, but then absorbance is A, and I don't want to have two A's. And so then we're going to add to it 3,000. Oh, wait. So now this is compound B. That is 16,420 times 1 times concentration B is equal to 0.380. So that's our first equation. Our second equation will be using the values at 540. So it uses the same format. So if we go in and plug all the things in, we would get at 540 instead of at 460. We get 37,680 times 1 times the concentration of A plus 2,320 times 1 times the concentration of B is equal to 0.0560. Now I have two equations, two unknowns. I'm going to solve it using elimination. You can use some other method if you'd like, or substitution. You can use another method if you'd like. So I'm going to take the second equation and solve for concentration of B and then plug it into the top equation so that I only have concentration A. So if I rearrange the second equation by subtracting the concentration of A from both sides, I'll get 2,320 concentration B is equal to 0.0560 minus 37,680 times the concentration of A. And then divide both sides by 2,320. I get concentration of B is equal to, I have to get a calculator and do that. So we divide by 2320. For the first one, we get 2.41 times 10 to the negative fifth minus 37,680 divided by 2320. 16 point, I'll just keep it extra decimals. We go 16.24 concentration of A. Oh, my face is blocking that. Let me make my face. We'll just make my face go away. 1 second. There we go. You're okay without my face. That way you can see things. Okay, restarted it. Okay, so now we've got an equation for concentration of B. We can plug that into our top equation for this value here. So when I do that, I'm going to go over, let's just make a little box over here to represent the other part. I did not leave myself a ton of space in this. There's 23. There we go. That's the best I got. Okay, so now when I plug those in, I get 2,750 concentration of A plus 16,420 times 2.41 times 10 to the negative fifth minus 16.24 concentration of A is equal to 0.380. Now I just need to distribute this across. I get 2,750 concentration of A plus, let's see what that is, 0.3957 minus 266,660 times the concentration of A is equal to 0.380. So now I just need to move everything to the same side. So we have that. So combine everything on the left side, on the CAs on the left side, we'll get negative 263,910 concentration of A is equal to 0.380 minus 0.3957 negative 0.0157. So we divide that by negative 263,910. We get that the concentration of A is equal to 5.95 times 10 to the negative 8th molar. So that's my first concentration. That's the concentration of species A. Now we need to find the concentration of species B as well by plugging into one of the other equations. I'm going to erase a few things on here. Okay, now we've got a little more room. So I'm going to plug it into my equation for CB over here. I gotta turn my pointer back on now. So we're going to plug it in for this value here. And so we get that the concentration of B is equal to 2.411 times 10 to the negative fifth minus 16.24 times 5.95 times 10 to the negative 8th molar. And this is going to give us a concentration in molarity. Okay, so times 16.24. And then I subtract that from 2.41 times 10 to the negative fifth, and I'm going to get 2.31 times 10 to the negative fifth molar. So these are our concentrations for B and A. So this tells us in this mixture it is predominantly compound B that is present compared to compound A.